Exhaust gases are expelled from the nozzle at high velocity, and the noise is generated by the turbulent mixing of these gases with the surrounding air. So the air to fully mix with the exhaust gases takes around 10 nozzle diameters. So in this area here we have some partial mixing, whereas down here we have full mixing of the exhaust gas with the surrounding air. We get small turbulent eddies close enough to the nozzle, and that creates high frequency noise, and we get large turbulent eddies about 10 nozzle diameters, and that creates low frequency noise. And low frequency noise travels furthest. This is what we can hear further away. I mean, if you can imagine a marching band passing by, you hear the drums coming first, and that's the low noise element. Okay, so the noise is generated by the turbulent mixing of the gases. So the magnitude of this turbulence is proportional to the velocity difference between the exhaust gases and their surroundings. And this velocity difference is known as the velocity shear. So shear, we've seen before, if this is a graph, so if I have something moving at that direction and then something moving here, this gradient here, that's the shear. So the larger this shear, the larger the turbulence. So one way of reducing that turbulence is maybe to add another layer where you would have maybe a mix of the fast moving air and the cold moving air, and let's just say it's there. Okay, and now the gradient is that. So there's less shear. Less shear is less turbulence, and less turbulence is less noise. So the idea then would be to try and mix this primary jet with some secondary or bypass air and create a annular mixing region, and that will significantly lower shear and less noise. So how are we going to create this second mixing region? Well, one way of doing it is to use lobes. So with lobes, the exhaust gases are divided into a flow through the lobes and out through a smaller nozzle. The air that comes out through the lobes, that mixes with bypass air or air coming around the engine here. So this fast moving air and slow moving air, they mix, and that creates this second annular mixing region. So the shear is going to be reduced, and therefore the noise reduced. Instead of lobes, we could also use corrugated nozzles. And here you can see the hot gases coming out, and they're directed in a way to promote mixing of the hot gases, and in this case the bypass gases. So you will get a mixing region here. We have a core region here, and that will reduce our shear. Finally then, if we talk about bypass engines. So with a bypass engine, we have slower moving bypass air and faster moving core air, and they can mix, and they can either mix outside the duct or inside the duct. This is called external mixing, and this is internal mixing. Recently, we've seen the addition of chevrons. So the chevrons help create vortices that help mix the air along here and here. And studies have found that the chevrons have been shown to greatly reduce jet noise by encouraging advantageous mixing of the free, fan and preliminary stream. I've also seen a paper where instead of having many chevrons, they've just used a small number of chevrons, a bit like that, maybe a bit like this. So this is one chevron there. This is another chevron here. And that was shown to be even more advantageous. However, I haven't seen an aircraft with those chevrons on them yet. So that's how we can reduce the noise from the exhaust stream. We can also use acoustic lining around the engine to help reduce the noise. And finally, I just want to say, like the fan creates a lot of noise. What can also happen is if we change the geometry of the inlet, if you move the inlet sort of to there, then the noise from the fan can rebound up and away from people on the ground or houses on the ground, and that would reduce the noise figure for the engine also. Okay, so there are the different methods of noise reduction for a gas turbine engine.